of patch solutions. This is rotating. Angular velocity. And we have to assume that the vorticity is non-negative. So each coefficient is bigger than or equal to 0. And omega is very low symmetric. The only possible for such solutions, the only possible case is that every patch is concentric, and we allow this vorticity to have different values. Say maybe it has the omega can be some number here, and maybe there's some empty region, and it attains another value, say 2 on the outer boundary and so on. So everything has to be trivial in this sense. The idea is quite simple. We just compute the variation, first the variation of the functional, and then choose the estimate for the function p that we defined. So I'm not going to go over the proof, but this is the main result for the patch solutions. And then now let's start another topic. So so let me first state the theorem. The goal of today's lecture and the lectures on Wednesday. So we know that if the vorticity, the stationary vorticity, okay, so if omega equals to 0, then it's stationary. Right? So if the stationary vorticity is non-negative, then it cannot have a non-trivial structure. But by allowing the vorticity to change sign, we were able to construct a non-trivial solution. So there exists non-radial stationary So there are two parts. The first part is that one can construct such a solution so that its kinetic energy is infinity. That's kinetic energy, which is in this case, because we are dealing with the incompressible order, there's no other, the density is just 1. So the L2 of the velocity, it's infinity, and also we can construct such a non-radial station solution so that its kinetic energy is finite. And there is even a stronger statement is possible. We construct a solution so that the velocity is so this is stronger because we are studying the patch type solutions. So patch type, its characteristic functions, and one can easily show that in this case, the velocity is continuous. And if the continuous function is compactly supported, then its L norm is obviously finite. Okay, any questions on the statements here? So, we'll find a radial solution. That is close the radial one. Basically, we look for a bifurcation from the trivial solution. So now, let me start from the problem 7. We are going to transform. We are going to put this question, like whether one can construct a non-radial solution. We are going to put this this problem into a functional setting, and then we are going to study the functional, whether the functional can have a non-trivial solution. So, because if the vorticity is non-negative, then we cannot find the non-trivial solution. So we are going to add some negative vorticity. And then we are going to study star-shaped patch solution. So let's consider a star-shaped patch. Consists of 2 layers. Here in the inner domain, we say the vorticity is 1, and let's suppose the vorticity is some negative number A. A is positive, so negative A is negative. So the vorticity has a negative value on the outer domain. Then we assume that the boundary, because we are looking for star-shaped domains, so the boundary can be parameterized in such a way. So this could be the distance can be written as R2 theta. And then the outer boundary can be represented by some function R1. Okay. So outer boundary can be parameterized by R1 theta times sine theta minus sine theta. And the inner boundary can be parameterized by R2 theta times sine theta. This is just a very typical way to represent each boundary for the star-shaped domain. So in this case, we can easily see that for each fixed the triple at 2. So once we fix a certain number, specific number for A, and specific functions for R1 and R2, then it completely determines the vorticity, right? then we can write the string function, which is the convolution with the linear potential. Or the velocity vector, which is given as the gradient curve of the string function, are functions of A, R1, R2. So this is very nonlinear, so I'm not going to write the explicit formula, but just you can use like divergence theorem or integration by parts. You can explicitly compute the expressions for the stream function and the velocity vector in terms of A and R1 and R2. So another thing that we are going to do is that we are going to replace R1 and R2. So for R1, we're going to replace it by 1 plus another function, small r1, and we are going to replace R2. So, as I mentioned, we are going to, so obviously, if R1 and R2 are 0, then large R1, large R2, they are just constant, that they don't depend on the angle theta, so it gives you the radial verticity. Then we get, so I'm going to abuse some notations, but we can think of the verticity as a function of A, R1, and R2. So I'm going to think of this as a function of A, R1, R2 is and because as I mentioned, we are looking for the non-trivial solutions that are close to the radial ones. We assume that this R1, R2 in some norm. So I'm not I'm going to specify like what norms we are going to consider for R1 and R2 later, but let's just have this in mind that this R1 and R2, they are small, so the corresponding vertex patch is just close to the radial one. Okay. Now then we have to construct a functional. So we define
A is the boundary value. A is the boundary value of formula.
No, it's on this region. Yeah, in the annular strip. Yes. So omega is 1 in the inner boundary area, and then omega is negative A on this strip, and omega is 0. Find the functional f of A and R. So here, this R denotes the pair R1 and R2. So it represents the boundary. The gradient of psi, which can be thought of as a function of A and R as well, times the tangent vector. And we look at this on the so let me use another notation. So let me call this boundary the gamma 1, the outer boundary. No. gamma out. And we call the inner boundary gamma in. So we look at the tangential derivative of the stream function on the outer boundary, and we also look at the tangential derivative of the stream function on the outer boundary, inner boundary. So this is a vector that has two components. And of course, this can be thought of as a function on the vertex strength on the outer domain and the boundary, right? If we fix A and R, then using this, we can fix the large R1 and large R2, and then you completely determine the verticity. And then you can write the gradient of the stream function in terms of A and R, and then we construct this solution. So the goal is to find some number A star and R star such that f of A star is 0, because if f is 0, then the stream function, its tangential derivative is 0. That means the stream function is constant on the boundary. And that's the condition they require for the verticity to be stationary. And also we require the stream function to be constant on the inner boundary as well. And we are looking for non-trivial solution. So we have to add another condition that the boundary is not trivial. If R star is 0, then the boundaries are just circles. It's trivial solution, but that's it. So we require the solutions are not trivial. Yes.
How do you solve the R
right. So we are always, so we look at this functional as, so we are always assuming that R, we always assume that the R, the average is 0. So let me write the, so for R1 and R2, we always look at the average 0 function. So yeah, as we mentioned, if this is just another constant that is not necessarily 0, then we can have a radial 1. But with this condition, the only possible constant value that R can obtain is 0. So if R is not 0, then the corresponding solution is non-trivial. Okay. So let me write some remarks about the stuff functional. So this could be the first remark. We always assume that the no, I'm not gonna write it. So let's see like what let's see the image space and the domain of this functional, and we are going to look at the we can think of this functional f as a map from the real numbers times Sobolev space HK. So we are assuming that the boundary is HK regular, and then what's the image space? So image space is gonna be HK minus 1 That's simply because we are taking the tangential vector that is the one derivative of the boundary. So we lose one derivative. There's k minus 1 here. And another observation is that f of a comma 0 is solution, trivial solution for any. Because if r is 0, then we get the radial vertices. So far, the functional setting looks very similar to the rotating functions that we went through last time with Claudia. Now then, let's recall the problem setting. So once we have this functional setting, then let's recall the Crandall-Robinson theorem. So first, let me recall the statement of the theorem. So let a functional we are given a functional here x and y are Hilbert spaces, and if f satisfies the following three conditions, if the functional input is 0, then for any real number, so I'm going to call this variable parameter. So for any parameter, the functional attains 0 value. So when you get this in a diagram, so let's suppose this the horizontal axis represents the parameters, and let's suppose the vertical axis represents the functional argument of space x. Then we have a trivial solution curve. This. So this blue line corresponds to the level set, the 0 level set, right? And the second condition that we need is that we look at the derivative with respect to the variable in space x. So we differentiate the functional with the function variable r that we are using there. E(r) of x. We look at this derivative on the points at the point on this trivial solution curve. So if the derivative is an isomorphism, then the implicit function theorem says that there is a unique curve that corresponds to the level set. So in this case, if it's an isomorphism at this point, then we cannot have a bifurcation because we already have a curve here. And the implicit theorem says that this curve is the only solution curve around this point. So we shouldn't have the isomorphism here, but what we require is that there exists a point. Let me use A naught, such that when you look at the derivative at this point, its kernel and the image curve are not trivial, but one-dimensional. So here the one-dimensionality, this specific number 1 doesn't really matter. It's just because we are looking for a bifurcation curve. If it were like 2-dimensional or 3-dimensional, then we are expected to find like bifurcation plane or higher dimensional manifold. But in this case, we have to allow the space, the dimension of the parameter is higher as well. But which is possible because we are looking at the one-dimensional parameter because we only pick this number to be our parameter, but we can use not only this vertex strength here, we can use the vertex strength in the inner boundary as a parameter as well. So in this case, we have 2-dimensional parameters, and then we can allow this kernel and image curve to be 2-dimensional as well. But let's just stick to the one dimension. And the third condition that we need is that the transversal condition so we already know from here that the kernel of the linearized operator at this point is one-dimensional. So we can pick a non-trivial element in this kernel. And we require the this guy. So without this partial A, this is an operator. So we can look at the directional derivative in this direction, in the kernel direction. And then when you differentiate with respect to the parameter, then we require this not to be included. So the image of this linearized operator, it spans almost every space except for only one-dimensional complement. And this guy can compensate that the missing dimensional the complement. Okay. And then for me, like this state, the third condition is the hardest condition to understand intuitively, but I will give you more intuitive reason why we have to require this condition just a minute later. So if the Kroner-Rabinovich theorem says that if the functional satisfies these three conditions, then we have a bifurcation. There is a curve. Of RS, such that each point on this curve corresponds to the zero level cell of the functional, and the solution, each solution is non-trivial. So there is a solution curve that passes through A naught. There is a curve, and just you can pick any point on the curve. Then in this case, the functional argument is not trivial, and it's a zero level, so our functional.
space is really state of the other assume that it has been zero or something.
Right, yeah, right.
So there's a space of this one.
Yes. Yes, so like, so let me use this 0 here. So here, say h k naught is the functions in hk such that so we can denote using this like sub index 0. So we always looking at the hk regular boundaries whose average is 0. Then it's not really clear at this moment whether they are really like whether the image is also like mean 0 space. But when you look at this point, we take the derivative. So its image has to be the mean 0 space as well. Because the derivative of something, when you integrate it, because the one-dimensional torus is when you integrate them, it has. Any questions at this moment? So I want to. So let me write down the functional here because I'm gonna erase that part. So our R is tangential derivative of the string function on gamma 1, gamma out. So the explicit expression doesn't really matter at this point. Or maybe yes. So, of course, we are going to apply the theorem. So we have to check if our functional satisfies these three conditions. But unfortunately, when you look for finite energy solution, then our functional doesn't really satisfy those conditions. We have to fix them. So let's see where the problem happens. So so the first one, it's very easy, as I mentioned. Just if you look at the radial vorticity, then it's just a 0. It's a solution. So let's look at the linearized effect. Okay. So let me write our functional in the following way. So if we fix the parameter, the vertex strength, and the boundary, then we have the string function times the tangential derivative. But what's the tangential vector on the boundary? So you can just simply take the derivative with respect to the variable theta. Then that is going to be so recall that R1 was 1 plus small r, and R2 equals R2. So we are going to have R1. So I'm going to just omit the notation of the subindex 1 and 2. So R prime times cosine theta sine theta plus R theta. Okay, so let me write in this. R1 theta R. 2 theta 1 plus R1 theta times, when you differentiate this guy, then we get negative sine theta. Sine theta. And then we have the same thing for the inner boundary as well. So I'm sorry for the notation, but recall that f has two components: the tangential derivative of the string function on the outer boundary and the inner boundary. And the outer boundary is going to just like this. So there's nothing complicated. I just take the derivative with respect to theta here, but we call it R1, large R1 is just 1 plus small R1. So when you differentiate R1 here, then we get just R1 prime, and then we have the sine theta and sine theta. And when theta hits this guy, this vector, then we get just negative sine theta. And then we have the same thing for the inner boundary as well. So this is gonna be so when you look at this times this, then this is the radial derivative of the string function. And we look at, we think of it as a function of A and R. And we have R prime. And the gradient of psi times this guy is going to be the angular derivative of psi. So we are going to have the same thing for the inner boundary as well, but I'm going to just treat it as one dimension. Is it okay? Is it understood? So let's see the derivative with respect to the variable r here. And we want to study the linearized operator at the trivial solution at 0. And then it's just a tedious computation, but one can show that this whole thing, if you look at the directional derivative, is going to be r psi a comma 0. The radial derivative of the stream function determined by the radial verticity times h prime plus minus 1/2 times Hilbert transform of h. So of course we are going to have like two components as well, and h is going to be okay. So the correct form is going to be like r psi on the outer boundary minus 1/2 Hilbert transform 0 0 partial r psi on the out and inner boundary minus 1/2 times Hilbert transform times h1 h2. Here h1 is the perturbation of on the outer boundary, and h2 corresponds to the perturbation in the inner boundary. And also it's not really right, because these components are not actually 0, but negligible. But just to make our life easier, I'm going to suggest that the linearized operator just look like this. So let's take this for granted. But in the real problem, when you explicitly compute the derivative, then these components are not 0. And
where does
how does it appear? it's just purely computation. So let me explain each term then. Like, okay, so imagine you take the derivative with respect to r, the whole thing. Then when the derivative hits this guy, then we are assuming that r is 0, so it vanishes. And if the derivative hits this one, then that gives you h prime, and then we have this guy. And when the r hits, so this, the angular derivative is also function of a and r. So when when the derivative hits this guy, then we have h times this one. But when at the trivial solution, the stream function is radial function. There's nothing left. So this Hilbert transform is coming from the contribution of the derivative of this guy. And this one is the gradient psi times this one. And so let me assume just one single patch, not that two-layer vertex patch. So recall that if the omega is just one single patch, then this guy is the convolution with the Newtonian potential. This is going to be d x minus log x minus y dy times 1. Particle like this, and then that can be the gradient is going to be d of the gradient log x minus y, and then you can do the green theorem, so that becomes the boundary integral of log something like this. I don't really remember the exact formula. But you know that you can like switch from this two-dimensional integral to the boundary integral, right? And then we note that this boundary can be represented by some constant plus r theta, sine theta in this way. So you can do the change of variables so that we integrate from 0 to 2 pi, and then we have like log of, so we look at the x, we evaluate the gradient of psi on the boundary. So x is gonna be 1 plus r theta sine theta minus the y can be changed to 1 plus r eta sine eta, something like this. And then this, the normal vector y is going to be the derivative, some nonlinear with respect to the r variable. And then we multiply this the negative sign of sine here. Theta, sine theta. And we integrate this with respect to the eta variable because I changed this y variable into this 1 plus r eta and stuff. So like this is nonlinear, but you can just look at the linear term only this part, and then you get the Hilbert transform. So this is just a computation wise. So let's consider like how does this expression work. So like of course we are studying the stationary patch solutions, but let me for the rotating patch solutions, like that the Claudia went through last time, like just a few weeks ago. So we know that for there exists like non-radial n-fold symmetry rotating patches. They are emanating from the angular velocity was like m-1/2f. I don't know if you already remember this, but that is what Claudia went through last time. But in this case, the functional was that the A from R. So right now, because we have only one simply connected patch, so R is not R1 and R2, so R is just one single number. So like 1 plus R. Yeah. Case, this functional was that the same thing, but we had the tangential derivative minus omega x times tangential derivative, which is the where tangential derivative like this, because this relative stream function has to be constant on the boundary, so its tangential derivative has to be 0. So what Claudia did was that we look at the 0 level set of this functional, and we look at the linearized operator. In this case, in this case, our parameter was not A, it was omega. In this case, when you apply this expression, then a trivial solution, its linearized operator is going to be the radial derivative of the stream function times h prime minus 1/2 Hilbert transform of h minus this is going to be omega times h. So when we look at this expression in the Fourier side, before that, so we looked at this at the trivial solution. So in this case, the verticity that we are looking at is radial one. In this case, you can very easily show that psi is 1/4 r squared, right? Indeed. Because on the radial verticity, the stream function is constant, which is correct because this is radial function. And then for this expression, the psi Laplacian, it gives you exactly 1. So for this radial verticity, the stream function is this one. Therefore, the radial derivative is just 1/2 on the boundary. Right? The radial derivative is 1/2 times r, but on the boundary, you get 1/2 times h prime. 1/2 Hilbert transform, this one. And in the Fourier side, this is 1/2 times in minus, this is going to be 1/2 times times sine of the frequency minus omega. Pi, I missed pi here. Pi omega in, which gives you in times 1/2 minus omega minus 1 over and over something like this.
Fourier multiplier.
Yes, that's the multiplier of this linearized operator. So then here we can see that we can just look at the wave numbers if n is if the multiplier if the frequency is positive, then when does this vanish? This vanishes exactly when 1/2 minus omega is equal to 1/2 this one, right? Because sine of n is always 1 in this case, so that we get the omega is 1/2 n. That gives us the same the bifurcation by angular velocity in our case. Yeah, I mean, I thought like this will give you like, it helps you to convince that the linearized operator of the stream function looks like this, but if it was not, then just forget about this. This is not very necessary in our case. But I just want to convince you that the linearized operator of this, like non-linear functional, is simply the radial derivative of the stream function and something like Hilbert transform. So it's not exactly Hilbert transform, but it behaves like Hilbert transform. Okay. Then let's go back to the stationary solution that our original goal. So our original problem here, and the linearized operator looks like this. And then let's observe the following. Okay, so let me start with the infinite energy case. So we are going to analyze this linearized operator for the infinite energy solutions. So here's a classical fact is that in R2, when you look at the Euler equation, the kinetic energy is finite if and only if the average or the integral of the vorticity is 0. So if we are looking for the infinite energy solution, then we have to impose the condition that the vorticity, its average is not 0. Right? So A. What was A? So A was the vertex strength on the outer boundary, so that the average is not 0. Then let's see what happens here. So we have to see like what is the radial derivative of the stream function. But because we're looking at this, every object at the trivial solution. So we have to look at this one, the omega is 1, and omega is number -a. In this case, the radial derivative of psi on the inner boundary is some positive constant on gamma 1, gamma in, right? Because psi is constant on the boundary because it's radial and it's subharmonic function, right? psi is subharmonic function. So when you look at the normal derivative, it's always increasing. So this psi r on the inner boundary is going to be positive. So this is a strict positive number. And we also can show that this C is something non-zero number on the outer boundary as well. That's because psi is harmonic outside on the exterior domain, and psi or no, let me rephrase this. You can just, because the verticity is radial function, you can just explicitly compute the radial derivative, and then you can show that the radial derivative is non-zero constant. Actually, you can determine whether it's positive or negative, and the sign actually determines whether the average of the verticity is negative or positive. Or you can look at the when you look at the psi, you can imagine the corresponding psi, then because if the mean is positive, then psi is increasing to infinity like log. So you can see that on the exterior domain, the psi, which is harmonic function, it attains the minimum on the boundary. In this case, again, the maximum principle says that the normal derivative on the outer boundary is the non-zero number. Okay. So in this case, the linearized operator that is going to be something non-zero number C out minus 1/2 Hilbert transform 0, 0, C in minus 1/2 Hilbert transform H1, H2 in this direction. Again, we look at this in the Fourier side, we look at the symbols. Then we have, oh wait, I'm missing the derivative. This is C out times derivative. C. So this is going to be some constants C out times IN minus 1/2 I sine of frequency 0, 0. We have the same thing. IN. Right? That's the symbol corresponding to this matrix. And then, as before, we pull out this vector I times n, so that some constant C out minus sine n over n 0, 0 C in sine n over n, something like this. H1. So, and here I didn't explicitly denote, but this constant is function of A, right? If we change A, then of course the radial derivative of the string function, it changes, it's a function of A, and the C in is also a function of A. Right. And then one can pick A so that the matrix is let me put this matrix to be M of M sub n. So that this matrix and has exactly one individual kernel image curve for only one. So how is it possible? So let's suppose we want this Mn has this one-dimensional kernel and image perp when n is exactly 3, say. Then we call that Mn was something like this. So again, let's suppose n the frequency is positive. So it's going to be 1 over n. 0, 0, C in, which is function of A minus. So we want to have a bifurcation for like threefold patch. So we pick the n to be 3. In this case, we can keep A so that Cin of A is 1/3, say, right? In this case, if this and this, unless they are equal, then we have 0 here when n is 3, right? And this matrix, 2 by 2 matrix, has exactly one-dimensional kernel and the image perp. And this happens only when n is 3, because if n is 4, 5, 6, then this guy is monotone. So this matrix never be singular. So like this matrix becomes non-singular for exactly one value of n, but for the other values of n, the matrix is non-singular, so we can have the one-dimensional kernel and the image perp.
What we mean is that for every n, you can pick one n for these characters.
Yes, for every n. So that's why, for example, in the rotating patch case, we can find the n-fold symmetric solution for any m is bigger than 3. So in this case, we can do the same as well. But like, and if m is, as I said, this expression is just like a simplified model. So in the actual problem, you have like another element here. But for that reason, if you pick n to be 2, then there's no bifurcation. But for any n bigger than or equal to 3, you can pick this A. So that's this matrix has one. And also, then we have to check this transversal condition as well. So let's suppose that, this is not really rigorous proof. I'm going to be rigorous for the finite energy case, but just I want to convince you that the finite infinite energy case can be done in a like standard way. So let's suppose we picked this A so that when n is equal to 3, this matrix has one-dimensional kernel and the image perp. And so this is going to be when n is 3. This is going to be some non-zero number, say 1. And this is 3. And we know that we picked A naught so that this constant C in A naught to be 1. Then what's the kernel element? So we can pick the M of 3 is just 1, 0, 0, 0. So you can pick 0 and 1 as the kernel of N3, right? And as I mentioned, N is non-singular. Any N that is not free. So we have exactly one-dimensional kernel, and its image is one-dimensional as well. And the H kernel element can be picked as like a 0 and say e to the I to the theta. Right? That's the because we look at this matrix in the Fourier side, so the corresponding element in the kernel space is going to be this guy, right? So the kernel of the linearized yes.
What was the this implies that essentially we are communicating the result of the bifurcation because either the inner boundary or the outer boundary produces this singularity. Does it mean that the perturbation is going to be a disk in one of the two?
No.
Or they both going to the form?
So actually, as I mentioned, this is not 0, 0. So when you pick the kernel element, this is not really like 0, something. Right. So the bifurcation happens like on the both boundary levels. Yes. But just I want to make things.
This third model, it seems like only the form one of the two.
Right. So this is just a toy model. So a span of 0 and e to the I. Okay. This guy. And the image is going to be image perp is the space that is not spanned by this matrix that is the same, right? 0 and e to the I3. That's it. And so when you look at the this guy, in this case, check the transversality. We look at the derivative with respect to A and B are F of A not 0, 0 e to the I, this guy. So we want this has some contribution to this missing the complement of the image. So we want this one has some the components of this vector. But when you recall that this and here, then that is going to be simply 0. So you multiply this vector to this matrix, then we get 0 and C in A minus 1/3 times e to the I3 theta. Of course, this is 0 when A is A naught because we picked A naught so that this constant should be exactly 1/3. But when you take the derivative in A with respect to A, then this is not necessarily 0. Right? Just you can imagine that, okay, this one. You have this radial verticity, and then we look at the radial derivative of the stream function here. Then when you change the constant here, then the corresponding the verticity, the corresponding stream function has the radial derivative as well. So this is how the the infinite energy case can be treated simply by the usual application of the Kernel-Rabinowitz theorem. But I'm sorry, I was too like hand waving this part, but I want to just focus on the finite case. And let me try to make the notation more neat and understandable this time. So from the infinite energy case, we know that the linearized operator, it was like the regular function, prime minus 1/2 of. This is the starting point. So, and then this one does not vanish when bifurcation happens. Right? That was the maximum principle. Then you have regular verticity. Then we know that the stream function is harmonic and subharmonic by region. So its normal derivative, the normal derivative doesn't vanish. But and this makes sense because recall that our functional it was the tangential derivative of the stream function. It maps r times hk to hk minus 1. That's what I mentioned before, right? So if your boundary is hk regular, then the image of this function has to be hk minus 1 because we take the derivative when you compute the tangential vector. And when you look at this linearized operator, that makes sense as well because we have one derivative here and we multiply it by some non-zero number, non-degenerate number. So df it also maps hk curve to hk minus 1. If A is picked so that the average of the verticity is not 0. So if you were looking for infinite energy case, then at the linear level and at the non-linear level, the functional behaves the same way. It maps, if your boundary is hk regular, then its image is hk minus 1. Right. So this is why we apply the Kernel-Rabinowitz theorem, because when we say the kernel and the image, they are one-dimensional, we look at the same spaces as the nonlinear level. But I'm going to prove very simple lemma. Let me just lemma. So let's assume our setting, and if A star and R star determines A stationary with such solution, then the velocity, its support of the velocity is equal to the support of the the verticity. Then what's the problem? In this case, okay, so I'm going to prove this later, maybe today or like tomorrow in the beginning. But the problem is that verticity has negative A outside and verticity is 1 here. And because in finite energy case, we pick A so that the corresponding the verticity has 0 average. But in this case, the velocity vector is 0 on the outer boundary, right? Because the support of the velocity is equal to the support of the verticity. So the velocity only survives on this domain, but it becomes 0 outside. So that means that the gradient of psi is 0 on the exterior domain. And because the gradient of psi is continuous, so the gradient of psi has to be 0 on this outer domain. Right. That means that this guy equals 0 on the outer boundary. So it's a degenerate case. So what's the problem? So we have that it's at the nonlinear level, it maps hk to hk minus 1. But at the linear level, it maps hk to hk. More precisely, because we are having two boundaries, we have hk boundaries, then its image is hk minus 1 times hk minus 1. The image on the outer boundary and the inner boundary, they both are hk minus 1. But if you look for the finite energy case, then its image is hk times hk minus 1. Because this is the contribution why its image loses one derivative, but because this guy vanishes at the trivial solution, so there's a regularity mismatch between the nonlinear level and the linear level. And in this case, the classical compactness theorem says that HK is a compact space HK minus 1. So in this case, because the image is compact in the Hilbert space, so its perp cannot be a finite dimensional space, right? So this is the critical part where we cannot really apply the kind of Robinson theorem. So I have like 5 minutes, so let me just prove this lemma is super quick, and then I will finish today's lecture. So proof. It's super easy. So we have, so in this, by the way, so here so here we are dealing with only the trivial solutions, right? Because the R is 0. But when you look at this lemma, we don't require this stationary solution to be trivial. So this R star can be just any stationary solution that is not necessarily trivial. So let's suppose there is a star, then maybe here, negative a star, and when you look at the corresponding vorticity average, this is zero because we are wait. So here, I forgot with finite energy. So I forgot to write this finite energy. So let's suppose there exists a star and R star that determines a stationary solution with finite kinetic energy. That means the corresponding vorticity has zero mean. Then let's denote omega by the supports and the vorticity. So this region is omega, and this is a stationary psi that determined by the star is constant. The outer boundary is gamma out. Why is this so? Because is right? Because it's stationary, the corresponding string function has to be constant in the boundary. Then we can very easily see that the Laplacian of string function is zero in this exterior domain outside the support of the vorticity, and psi is constant on this boundary. So the maximum principle says psi is constant. So it's greater than psi is zero. And actually, there's a missing part. Yeah, but actually, there's a missing part because the omega complement is unbounded domain. So what if psi has maximum or minimum at infinity, not the boundary? Because that's the case. Because when you have a disk, right? When you have a disk, and then you can imagine psi to be log of x, then it's constant on this circle. But psi is not really constant. Its gradient is not zero on the exterior domain because its maximum is attained at infinity. But this condition, in other words, we have the Laplacian of psi zero. This prevents the stream function to have maximum or minimum at infinity. So with this condition, its maximum and minimum has to be attained on the boundary, and then we can apply the maximum principle to prove this. Yes, I think that's the proof. So I'm sorry, today the lecture was very live hand waving, but I will be more vigorous and clear on Wednesday lecture. And then I will start from here, and then we will go through how to prove the finite energy stationary solution. Thank you very much. Yes.
The structure of these deformations. I mean, I agree that the matrix is not, it's more perturbation of this one.
Yeah, right.
So this means that when for certain values of K, it's the outer boundary that produces the deformation, and for certain values of A, is the inner boundary that produces the bifurcation.
I mean, ideally, that's possible. So, yeah, so you're asking, okay, so we have C, out, A, take like 1 over n, 0, 0, C out, in, yes, C in. Okay. So we can choose A, in one case, this to be 0, or the other case, it could be another A, so that this case to be 0. I mean, like, based on what I was talking, it's possible, but when you actually compute, then there is no such A. And I don't know actually why, but there is only one A. No. Yes. I think you're right.
What they mean is that for such things is the outer boundary more deformed than the inner boundary that resembles certain. Have you seen numerical simulations of this?
No, we did. I think Javi did some numerical simulations, but I didn't really.
It looks to me that if it's the first one, it's going to be that the inner thing will look like a circle and just.
Can you say the question? I couldn't hear the question.
Right.
Jamin, can you repeat the question? Or anyone?
It's not hearing my question. You can repeat the question.
Yes.
Or type it.
Because the linearized operator looks like this. It was a toy model. But in this case, let's suppose we pick A so that this guy is 1, but this guy is 0. So the kernel is actually on the kernel elements, it changes the inner boundary only. So in this case, when you look at the R1 and R2, so the large R1, it was the outer boundary, it was like 2 plus R1, and the small large R2 was the inner boundary, it was like 1 plus R2. But in this case, the R1, yes, R1 is gonna be, its size is gonna be like, say, epsilon squared, it's much smaller, size epsilon squared, while R2 its size is going to be epsilon, something like this, right? Because the majority portion has to be in the kernel element, and the kernel is just, yes, in this way. So that's your question, right? Yes. Right. But actually, as I mentioned, this is not really 0 in the problem. So it was like, say, it was like, C out A minus like 1 over n, and this guy is like 1 over 2 to the n, and say 1 over 2 to the n, and C in. It was something like this. So if we restrict n to be some finite number at 3, then this matrix doesn't have really like trivial. Right. Yeah, so exactly. I just said if we look for the large symmetry, large ample symmetry bifurcations, then maybe I think we can see that the outer boundary perturbation dominates the inner boundary perturbation, or the other way around. Yes, that would be possible for large n.
Still,
Chat? Okay.
Can you ask whether this type or
Okay.